Hi, this is Mr. Tegmeyer again, and this is part 3 of the Introduction to Electricity. In part 1, we covered atomic theory, and in part 2, we covered some mathematical relationships, and we talked about Ohm's law. And we ended that presentation with Kirchhoff's laws. And here we're going to go through some examples of how to apply Kirchhoff's laws and Ohm's law to series circuits. So let's get started. First, let's talk about what is a series circuit and what is a parallel circuit. And here you see some basic diagrams down below. A series circuit on the left basically just has one path for electricity to flow. And you see the red rectangles? Those red rectangles can be anything. Those can be batteries, those can be light bulbs, a lot of different things that it can be. It can be inductors or capacitors or all kinds of other things. So those just are generic components. So in a series circuit, there's one path. So if I cut that path, current does not flow. On the other hand, if you look on the right-hand side, let's say I have a battery in the leftmost rectangle. If I have a battery, that electricity can flow in three possible paths around the loop, which means if I cut the wire on two of those loops, I still have electricity flowing through the other one. So we're going to take a look at series circuits in this presentation, and then in part 4 we'll talk about parallel circuits. So let's get started. So as I mentioned, a series circuit is just simply a circuit where you have one path. If I cut that path, then there's no current, there's no electricity flow. So for example, if I take that light bulb out, everything goes dim, there's no electricity. Let's take a deeper look at a series circuit. So one cool thing about series circuits is that the current is constant throughout. So no matter where I measure my current, it's the same everywhere. So we remember for Ohm's law, we have current that we're concerned about. We're concerned about voltage, and we're concerned about resistance. So if current's the same everywhere, then let's take a look at resistance. So for a series circuit, the total resistance equals the sum of all the resistances that are in that circuit. And similarly, the sum of all the voltages across the components add up to the total voltage. So here's what that means. So if we take a look at the diagram below, we see V total, which is essentially a battery, or it could be some other power supply source. In class, we will use power supplies. So this would simulate a power supply or a battery. And here we have 12 volts for that. And as we go around clockwise to the right, we see the first resistor, R1, has a value of 220 ohms, and the one on the right, R2, has 470 ohms. And then finally, the third value, R3, is 1.2 kilo ohms, K being 1,000. So 1.2 kilo ohms is 1,200 ohms. So what the voltage, Kirchhoff's voltage law says is that if I add the voltage across the first resistor plus the voltage across the second resistor plus the voltage across the first resistor, those all equal the total voltage, or 12. So how do we figure all that out? Let's take a look. So one of the first things we do is we have to figure out what all the totals are for the complete circuit, and then we can take a look at the individual components. So the first thing we want to do is we want to figure out what the total resistance is. We know that the current flowing through each component is the same. So I total is the same as I1, which is the current flowing through the resistor at 1, the first resistor. That equals the current flowing through the second resistor equals the current flowing through the third resistor. Current is the same for a series circuit. And then finally, we want to look at the voltage, we say voltage across. That's the correct terminology. Voltage across each component. And then finally, we're going to verify that all those things do indeed add up and verify Kirchhoff's law. So let's take a look at resistance. So in a series circuit, all the resistances just simply add up to be the total resistance. So we simply just take 220 ohms plus 470 ohms plus 1200 ohms, and we get 1900 ohms, or 1.9 kiloohms. But we want to know the current through each one. So we take I total equals V total over R total, but we still really don't know V total, or do we? Actually, we do. That's given to us. That's 12 volts. So here we say, I don't know why we have 1.89, but it's actually 1.9. So 12 volts divided by 1.9 is 6.3 milliamps, or 0.063 amps. So therefore, we can say that the current everywhere is 6.3 milliamps. But we also want to know the voltage across each component. And here we can use Ohm's law. But let's take a look at each component. So at 1, for the first resistor, we just apply Ohm's law. We have 6.3 milliamps times 220 ohms, and we get 1.4 volts. That's at R1. So at R2, we plug in the current. It's the same current. We just use the resistor value for R2, which is 470, and we get 2.98, or 3 volts. And for R3, we apply the same thing, but instead we use 1.2 kiloohms, or 1200 ohms. Make sure that you convert that to 1200, and we get 7.62 volts. But now we want to make sure that all those voltages, do they really add up to V total? Because we didn't use V total on the last page. So we plug in all of our values, and for V1, the presentation here uses more exact numbers. We have 1.4 plus 3 plus 7.6, and indeed that does equal 12 volts. And that concludes part 3 of Introduction to Electricity.